What's up, everyone? It's Miss Wesley back for some calc time, and we are talking definite integrals, and we've been working hard on finding area under a curve for the past few sessions. I'm looking at definite integrals packet page 19, and I want to scroll down to a problem not the likes of which we have seen yet, where it says you're supposed to sketch a region and shade the area between two curves, and we're going to use definite integrals to help us do that. I would have started off today's session with a joke, and I would have told you guys a steak joke, but they're never really well done. Let's look at number 5 together. First, you gotta sketch the graph. Let's see a picture of this situation. So it's between the curve y equals x squared and the line y equals 2x. Let me draw the line first. So I know that goes straight through the origin, and I'll use the slope, rise over run, up 2 over 1, to just sketch the line. Y equals 2x. Okay, so that's not too bad. Next up, we'll add to the picture the curve y equals x squared. I know that's a parabola that opens up, goes straight through the origin, and it actually intersects the line at a convenient point. This is going to curve up and through, and that is not my best work. I apologize for that, but 1 squared is 1, so I've got a dot here. 2 squared is 4. You have an intersection point, actually 2 intersection points if I circle both of them, between the curve and the line. Can you shade the area and close in between them? We haven't, like I said, we haven't really seen a problem like this before, but we want to find this area here. Now, what's cool about drawing a careful picture is that you do have the intersection points. I want to show you the steps for finding that on your own right underneath of the graph. Let's say we were iffy about where those two curves hit each other. So I'll label this intersection points. And we can find those x values by solving the two equations together like a system. So if y has to equal this expression and y has to equal that expression, we can equate those two x expressions. We'll say x squared needs to equal 2x. Where is the line? 2x going to meet the curve, x squared. Resist the temptation to divide both sides by x. You'll lose a potential solution that way. Instead, let's move everything to one side of the equal sign. We'll factor it to get the two intersection points that we actually already knew about. 0 is a solution to that equation, as is 2. So 0 and 2 are going to be our limits of integration here. We want to find area over a certain interval of x values. I'll use a for area equals the integral from 0 to 2. So I kind of have those limits of integration set now. The integral of what? Here's the question. Well, we haven't seen one of these yet. Let's think about it this way. Shouldn't it be equal to, if I took all the area of this whole triangle under the red curve, so that'd be the area from 0 to 2 of 2x taken with respect to x. And that's too much area. That's the entire triangle, and I want to lose this little piece of it so that all I have left is the shaded region. What if we were to do this? Could you subtract a definite integral from 0 to 2 of the bottom function? So the bottom function is that green curve, x squared dx. Like I said, we haven't seen one of these, but that will do the trick. And I'll label this here. You can take the integral from 0 to 2 of the top function. So FCN, abbreviation for function, is the curve or the line that's bounding the region from the top. And the rule is, for area between curves, you can subtract all of the area here that I'm just shading in red below the bottom curve. If we subtract this off, what we'll have left over is the exact area of that sort of banana shape or that crescent moon that we want left over. So I'll put bottom function here. I wanted to show you this method, and we'll get more into it actually in the next unit or so, but we have enough information to solve this definite integral. And I actually could combine this into one expression, but for now, I'll keep things separate. So we'll say, first, can you integrate 2x? So integral of 2x, we'll say, is just x squared, right? 2 over 2 times x squared, evaluated from 0 to 2. And we want to subtract the integral of x squared, x to the third over 3, evaluated from 0 to 2. Okay, so that's your integral calculation. We'll do the plug-in, start with the top number, so 2 squared minus 0 squared. And you're subtracting the area under the green curve. We'll plug in a 2 and get 8/3 minus another 0. This is just like saying 4 minus 8/3. And you can always leave your answer as an exact fraction or a rounded decimal. I'll say 4/3, 1 1/3 units squared, or 1.3 repeating. afterwards. And what you'll see is, I want to show you one more example of this as a follow-up in a little bit of a tougher picture to draw. So I'll use the calculator or Desmos to help me see it. Can you flip over? Let's go a couple pages ahead to, what page is this? I guess 21 of the packet. And we'll try one more to solidify it. Let's look at 10, at least the setup of this problem here. It says find the area of the region bounded by this curve, which, think about the curve first as you get into this question. What shape should this be, just by looking at the equation? I'm thinking parabola because x is squared in the highest term, and it's going to open up because I see a positive leading coefficient. And then as a prediction for this curve, you've got another parabola that opens down. And again, same directions, just like in number 5, we want to find the area between them. It says graph the functions on your calculator first. Because it's so easy to mess with the window on Desmos, I'm actually going to go to Desmos for this one. For my first equation, I'll go ahead and type in the parabola that opens up. So I'll use x squared, y equals x squared, minus 3x, plus 2. Plus 12, how about? Okay, so that one's off the graph, right? I didn't do anything wrong. I'll just have to kind of move the, or change, maybe zoom out a bit so I can see that parabola that I had predicted to open up. Let's go ahead and type the second equation into the second function. So we'll go negative x squared plus x plus 18. Let's see if these actually do intersect. Sometimes they don't, but these two are going to intersect. Keep these points in mind, but we'll show the work for getting those intersection points. Feel free to zoom it out so you can really see that this is going to be our shaded region right in between. On my packet, I'll just draw a rough sketch of what I saw. So it looked like you had this one parabola that opened up and another parabola that was opening down. And this is a zoomed out version of the curve, but in red, I will shade the region in question. We want all this area between the two curves. And I say step 1, I know Desmos gets us the intersection point really nice, but step 1 is, if we want to find the area, we definitely need limits of integration. We need to find those intersection points in terms of the x value so we know what to plug. So here's some good algebra practice. I'll just put the work right under the picture here, intersection points. And again, we're just confirming, if we're calculatorless, there will still be a way to find out where the graphs meet x-wise. Set the two expressions equal to one another. So I want to find out where the curve x squared minus 3x plus 12 is going to equal negative x squared plus x plus 18. Okay, my best advice, pick a side to move all the terms to. If we want to keep the leading term positive, I think a good choice would be the left side in this case. So how about minus 2x squared? Let's subtract an x over to get minus 4x, and then subtract an 18 to get minus 6, equaling 0. Factor or quadratic form to solve, you can GCF out of 2, minus 2x minus 3, and then this will factor pretty conveniently to get, I think, the same values, hopefully, that Desmos was giving us, a 3 and a 1, with the 3 negative, the 1 positive in the factoring, with 2 solutions. Positive 3 the graphs are going to meet, and negative 1 the graphs are going to meet. So 3 and negative 1. So 2 huge advantages to looking at this picture before we get the problem started. Huge advantage number 1 is we just got the numbers. Where those 2 graphs meet are going to give us the lower and the upper limits of integration. Huge advantage number 2 is it helps me visualize which one of these functions is bounding the region from the top and which one's bounding the region from the bottom. So it looks like if I'm going to use the rule we used on the last problem, I have to do top function minus bottom function. And here I'm going to do it all in one integral because it's fine to do that as long as we're integrating it from 1 to 3. It looks like the top function is actually the upside down parabola. I'm going to call this expression bounding the region from the top, and this other expression is going to bound the same exact region from the bottom. So let's do top function, x negative x squared plus x plus 18 minus parentheses, I'll put the whole bottom function in this next slot. So x squared minus 3x plus 12. All integrated with respect to x, and that should do the trick. And for your notes, let's label it. I'll say function that bounds the region from the top, and then function that bounds the region from the bottom. Okay. From here, we've done all the hard and I'd say creative work of this problem. Now it just becomes an algebra and a calculus exercise to be able to take the definite integral. Let's show the simplifying here. Let me move myself out of the way too. So you've got integral from -1 to 3. And let's combine the like terms. So really, let's get rid of these parentheses. -x squared plus x plus 18. And I'm going to distribute this negative sign in to get -x squared plus 3x minus 12 dx, like that. Here we've got an integral from -1 to 3, scooping up the like terms, of -2x squared plus 4x, and then 18 minus 12, I think plus 6 is what we want to integrate. And let's show that integral before we do the plug-in. Integrate now. So -2 divided by 3, x to the third, as we take an integral, plus 4 over 2x squared, so 2x squared should be your next term, plus 6x, the integral of 6, all evaluated from -1 to 3. You're plugging a 3 in first, then you're carefully subtracting what you get when you plug in a 1, -1 rather, I should say. Feel free to pause the video and try the calculation on your own. Tune back in and check your answer with this. Here's a decimal, about 21 1/3, 21.333 units squared is going to be the area. So these get a little bit more complicated because you've got the top and the bottom function to be involved. 11, we're not going to solve fully out. I just want to show you the setup of 11 just so that you can see that a situation like this is out there. Here are your two equations, x to the third minus 3x squared. So you have some kind of S-curve. And then you have this other function that's a parabola that opens up. I just want you to see this graph on Desmos so we can talk about it for a tiny bit. So I'm going to go in and clear out my equations from the previous problem and type in the cubic function first, x to the third, and I am pretty zoomed out here, minus 3x squared. And then in the second slot, it's going to be what? X squared plus 5x. So here's what I see. It's kind of funny because if I zoom in, I can see part of the region here is going to be this little sliver in question. That's bounded by the two curves. But do you see a bigger portion from 0 all the way up to the next intersection point? Yikes, I'm zooming the wrong way. That also needs to get added. I want to draw a simplified version of this on your packet as I show you the setup. So you have, and I apologize for my artwork here, you have a parabola that opens, let me give this a try, that opens up, goes right through the origin, right? That's your one curve. The other one, and this is not drawn to scale by any means, is an S-curve that hits this parabola 3 times. It comes up through the origin, bounces down, and goes back up again, yikes, to hit the curve again. So again, I am apologizing for these technical difficulties, but I do want to shade this region in question. And there's actually 2 portions of area that we care about. We care about this little shaded area in between in green and this other shaded area in between. So what's funny about the setup of this, and we're not going to actually solve this integral, but we will show that setup. If I looked on Desmos, or if I set these two expressions equal to one another, I get, count them, 3 intersection points. I get one at 0, I get another one at -1, x equals -1, and I get a third one at x equals 5. What's funny about this one is you can't necessarily say that the red function's always the top or always the bottom. It switches. They flip-flop in between at 0. So this is not like problems you'll see on your homework for now. We'll get more into this later in the unit. But just to show the setup, you could set up 2 integrals for this area. You could say area equals, well, in one portion, from x equals -1 to 0, it looks like the S-curve's on top. So the top function is going to be x to the third minus 3x squared. And we're going to subtract the bottom function, minus x squared plus 5x. That would be the first part of your integration. You've got top minus bottom. And I only chose those 2 in that order because I looked at the picture, and in that particular area, the S-curve was on top and the parabola was on the bottom. Plus, let's add a second integral. For this one, let's go 0 to the next intersection point, 0 to 5. Because the 2 functions have flip-flopped, that's what complicates things. Now your top functions, the x squared plus 5x, and the bottom functions, the x to the third minus 3x squared. dx. You flip-flopped. This now becomes t for top and b for bottom. Again, not important that we solve this whole thing out. Just wanted to show you one other picture of what could occur. Enjoy your day. Talk to you soon.